So welcome back. The aim today is to continue the discussion we had yesterday on many-body perturbation theory, where we were setting up the basic equations. And we're just going to remind you of some of the equations which we put up and the equation we landed at. This equation here was just a rewrite of Schrödinger's equation. And it didn't look very promising from a practical implementation point of view. But let's quickly remind ourselves of some of the technicalities. So what we did yesterday was to define different quantities. So let me just quickly remind you of the quantities which we defined. So we defined this projection operators, and this P is normally referred to the model space. So this is the space we are interested in. It doesn't need to be one-dimensional. It can actually be a space which contains many more Slater determinants. So the states which you see here, they can be one-body states, or they can be two-body or many-body states. So this is just a general state. In our case, we are looking at the ground state of a system. And so we are targeting that one. And we have also assumed that this basis, which we have opted for, is an eigenbasis of the operator H0. And this is given by phi 0. And this W0, the way we have defined it previously, is just the sum over all the single particle states below the Fermi level, all the field states. So we have this subscript I to indicate that this is a whole state. Then we had an operator which is normally called the exclusion operator. So that projects out your wave function to the space outside of this model space. So this is normally called, it has a name here, it's called the model space. And this Q is then given by the sum over all the other states. So we just put M different from 0, and we have our orthogonal basis. So this is a matrix. And then what we have in addition is that P and Q commute. Sometimes I forget to put the hats on here. And this is equal to 0, which means also that PQ is equal to 0. We also have, since the states we have chosen to make these projection operators, so these are projection operators due to the definition here, is that these operators here, they, due to the way they are defined, they also commute with the Hamiltonian for the non-interacting system. And this is something which we use then to redefine the energy of the system. So when we did an FCI calculation, we defined the reference energy as the expectation value, this W0, plus what we normally call the expectation value phi 0 of HI, which is the interaction piece. And this is something which we would write out as a sum over I, and then we have an I, H0 of I. And we are assuming that this basis I is an eigenbasis of H0. It could be, if we have a Hartree-Fock basis, we normally have to redefine this one. And if we are looking at a specific new vacuum, we are going to rewrite this quantity. So this would be a half of Ij, and then we would have an Ij of V of Ij. And this is anti-symmetrized. This is in case we didn't have a basis with respect to a new core. And when we look at the basis with respect to a new core, this H0 is actually given by this operator F. And we could assume then that this basis is an eigenbasis of this operator F. So we can leave that unspecified. And this contains then the same term which we have here. So this is the quantity which then defined the correlation energy, which is given by E minus E0 ref. So this is normally called the correlation energy. Now, when we did many-body perturbation theory, MBPT, we had a slightly different change. So today we are actually going to map the energies which we get and then link that with the correlation energy in FCI theory. In this case, what we had was that this was given by E minus this W0. And then what we're going to see today is that the different contribution to perturbation theory, they will allow us to make a link with the reference energy, the way we have defined it for the FCI calculation. Let me also quickly remind you that this delta E, when we had only a two-body interaction, that's something which we could rewrite as an AI. And then we had these coefficients, which represent a one particle, one hole excitation. And we had this matrix element here. That was one of the terms. And then we had plus, and then we had the sum here. And now we are not putting in a factor of a half because that will come in the definition of the coefficients. And in this case, we had a sum over two particles and two holes. So there's a two particle, two hole excitation. And this would stop at the level of a two body interactions. So this is the way, if we then diagonalize, we can immediately calculate this correlation energy. Actually, there's no point in calculating the correlation energy because when you diagonalize, you get E and you have the reference energy. And to calculate this correlation energy means that you have to have a quadruple sum. So but you could actually check that with your eigenvectors that you're getting the same energy which you get from diagonalization. Yeah, that's a useful check of your formalism. Okay, so what we did yesterday was actually to rewrite everything, and we found an expression for the wave operator, which we ended up with an expression in the following form. So this is the true wave function, which we are assuming now, due to this intermediate normalization trick, we can rewrite this one in terms of a set of coefficients C0m of this phi m. And we could rewrite this one as an expansion from I equals 0 to infinity. And then we had this operator Q, and we had this W, this quantity, which we defined as just a parameter, which we can choose later. And then we had an omega minus E plus the interaction term. And this is to the power of I. And then we have phi 0. And when we then calculated the energy, this delta E then is actually going to be given by this energy, this operator, which we have here, multiplied with HI, and then multiplied with psi 0. Yeah.
Did you call the list of the post-Hartree-Fock method?
Yeah.
So when you write this sort of expansion, phi 0 here, is it often like in the Hartree-Fock basis?
So
in the computational basis?
We leave this undefined.
Okay.
So it's normally called post-Hartree-Fock because typically you would replace the computational basis with a new computational basis, which is the Hartree-Fock basis. Right. So you can always choose the basis you want.
Yeah.
So if you run a Hartree-Fock calculation, you have a new orthogonal basis, and you could say that this is now my computational basis.
Right. So in practice, you have to like often run a Hartree-Fock calculation to find the coefficients, and then you run this.
Yeah. So the thing now is that when you have a Hartree-Fock basis, the thing which would change, all these matrix elements will then clearly change because you would have to modify your matrix elements as well. So I don't know if you remember when we looked at Hartree-Fock theory, when we wrote the energy in the Hartree-Fock basis with respect or in terms of the original computational basis, then you got these coefficients which you had to multiply the one body part and the two body part. And so when you run a Hartree-Fock calculation, you actually have to generate a new interaction or new interaction matrix elements. That's a more precise way of saying it. So now we just leave it undefined. And we just say that we have a computational basis. And clearly, if you have a Hartree-Fock basis, what we know then is that this term here actually disappears. Because in a standard restricted Hartree-Fock, this is actually the condition which we put, that these matrix elements should be 0. And then you only have this term here. And then these matrix elements would have to be computed with the Hartree-Fock basis. These coefficients you see here, these are the coefficients from the many-body calculation, the FCI calculation. They are not the Hartree-Fock coefficients. So they are the coefficients you get when you diagonalize. Now, what we are going to do now is actually to build up these coefficients with many-body perturbation theory. So that means order by order, we will get a correction to these coefficients. And that's pretty useful to see, actually, because that links many-body perturbation theory with the FCI calculations. Now, the other thing which we did then when we have this expression here, so just let me bring this up, because then we can complete everything. And as Håkon asked, I mean, we just leave the basis, the computational single particle basis, and also the many-body basis, we just leave it undefined. We just assume that there is an orthogonal computational basis. And then this H0 could now contain the Hartree-Fock operator. So we're also free to define this H0. That is just an operator which gives us a handy basis and is a solution to a one-body problem, where the one-body problem can have information about the forces, or it's just an adequate one-body problem, which gives us an orthogonal basis, which may mimic the physics which we're interested in. So in this case, what we end up with then is this expression here. So we would then have an h of I multiplied with q of an omega minus h0, and then we have omega minus e plus h of I power of I, and this is given by phi 0 here. Now you can, if we now look at these equations, there are two ways, because this parameter omega is a parameter which is undefined. So one of the standard approaches is normally called Brillouin-Wigner perturbation theory. I don't know if I'm pronouncing Brillouin correctly. This is normally written as a BW. And in this case, this parameter omega is given by the exact energy. So when you look at these quantities here, we have an expansion in the exact energy. So this is clearly not a desirable quantity. But if we now look at what we have here, so let's just rewrite these equations a little bit. So if we now look at the equations and we write them out, this delta E, what we get then is the following. So we have a phi 0, and then we have H1 plus, and then we have H1 multiplied with this operator Q, and then we have an E minus H0 multiplied with Q multiplied with H1. And then we just continue, and we have higher and higher orders of E minus H0, Q of H1. We get a new Q here, and then we have 1 divided by E minus E0, H0, sorry, Q of H1 plus plus. And this ends with a last term here, which now is a infinite. So this actually goes to infinite order. Now what you can do then, when you look at this equation here, is to redefine the wave function for the state we are looking at. And this is now given by 1 plus q. If you look at the wave operator itself, or the wave function itself, we can actually rewrite that in terms of an operator. So we have E minus H0, and then we have Q times H1, Hi, plus, and then we have Q of 1 divided by E minus H0 of Q of H of I. So I'm going through this because this is going to give us a kind of feeling of how the wave function is going to look like. And then it just goes on all the way. And this is multiplied with phi 0. This is often rewritten in terms of a quantity which is called the wave operator. So now we define the wave operator for Brillouin-Wigner perturbation theory. And later we are actually going to write this one in a diagrammatical representation. So that's something which we are going to do next week. And that allows us to write this operator in a compact way. And then we are going to take contractions between that operator. And if you look up here, there's going to be at the end, there's going to be an interaction matrix element. So we can represent this operator in a diagrammatical form in a compact way. And then at the end, we perform the contractions with the interaction. So we define this quantity, which is called the wave operator. We've actually met this before. We called it actually the correlation operator, because this brings in correlation. So in that case, we define this quantity omega of E because it depends on the exact energy. And you can see now, if you look at the wave function here, you can actually rewrite this as a Q of 1 divided by E minus H0. And then you have a Q of H of I plus, and you see now the only thing I'm doing now is I'm pulling out these terms of Q of H of I, Q of 1 of Q of H of I plus plus. So this would be now the expression for the wave operator. And that means that I can actually, if I also define, so if I define the wave function now, what I would have is that psi of 0 is now going to be given by this omega of E multiplied with the state phi 0. That means also that the energy, which I'm looking after, this correlation energy, is going to be given by phi 0 multiplied with the matrix element, which multiplies with the operator, and phi 0. So we can perform further manipulations here. So it means that the total energy in this compact way is written in terms of this W0 plus phi 0. And then I have H of I multiplied with this wave operator and phi 0. So the wave operator can then be seen as a way to represent the exact wave function in terms of an expansion, a perturbative expansion, which contains the interaction divided by the energy, which we have as an unknown quantity here. Now, if we now look at what we have, we can now redefine this delta E in terms of contributions to different orders in the interaction. So we would then rewrite this one as a 1 to infinity. And then that means that this delta E is going to have terms of this type. And if we now look at the first order term, 1 here, if you go back to the expression we have for the energies, you see now that you have a 1 here. That multiplies with this one. So that means that the first order term, the one which is first order in the interaction, is simply this term here. And this is something which we have already calculated. If you remember what we did in the beginning of the semester, this was the same, since this is now a determinant, which is an approximation to the ground state. This is simply the sum over all these states here. So we would have a matrix element for this many-body expectation value. So we would have a matrix element which involves 2 single particle states at the time. And if you now look a little bit carefully at what we have, what you can see now is that our old reference energy, which we defined for FCI, is actually now given by this omega 0, which now could be a Hartree-Fock basis or just a plain orthogonal basis, plus this delta E to first order interaction. So that means that the correlation energy which we have in FCI, that is actually, when we now take away the first order term, this is actually going to be given by I equal 2 to infinity in terms of this delta E of I. So if you spool back and you look at what we defined when we did FCI, in FCI theory, we had an expression which now contained already the expectation value with the ansatz for the ground state, which is contained in this part here. So when we link this with many-body perturbation theory, this part here has a contribution from the first order term in interaction plus the unperturbed energies, or the energies which are the sum of the single particle energies. Because that's the expectation value of a one-body operator, where we have assumed that the basis is an eigenbasis of the one-body operator. Does that sound clear? So this is just to make the links, because sometimes people, when they talk about correlation energies, it can be a little bit confusing, because in perturbation theory, you have a slightly different definition, because you actually start with this omega zero, and you want to have a series expansion, which depends only on known parameters. Now, the drawback with the Brillouin-Wigner perturbation theory, it looks very nice here, and you can actually rewrite this in a very compact way. I'm going to show you how you can rewrite that in a compact way. The problem with that expression is that it depends on the exact energy, which we don't have. So it looks like as we haven't achieved anything at all. But it's a nice regrouping. However, people can actually solve these equations iteratively by assuming a guess for the energy, and then just keep iterating. Now, the thing which is interesting for us now is also the second order term. If we take a look at that one. So the second order term is now something which contains, if we just write it out, this is going to be a term which, when we write it down, it's going to contain a sum over these intermediate states, different from the ground state. And then we are going to have a matrix element phi 0, and we have h of I, and then we have this phi. Now I'm writing the explicit matrix elements, phi of m, and this h of I, and then I have to sneak in a phi 0 here. So this is the matrix element to second order, and then there is an energy denominator. And this energy denominator, when we now look at, so let me just write it out here. So this contains now E minus, and then the energy of Wm. So how do we get that one? So what we had originally is this quantity here of E minus H0. Now, when you expand this, what you get then is H0 acting on Q, H0 squared acting on Q, and so on. And we know that H0, when that acts on one of these states, this is equal to Wm multiplied with a state, because these are eigenstates. These are still many-body states. Keep that in mind. So here we haven't made an explicit calculation of what these quantities are. So when I now write out the denominator in a Taylor expansion, I'm getting the operator. First I get 1, I have the operator, then I have the operator squared, and so on. And when I calculate the eigenvalues of these quantities, what I'm getting then is just, instead of the operator, I get omega or Wm. And then that means that I can rewrite this denominator as you see here. So this is the way the expression is going to look like for many-body perturbation theory with Brillouin-Wigner. And we can continue like this to third order, fourth order, and so on. The hope is obviously that this will converge. We are not going to look at the explicit expressions yet, because I want to wait a little bit till we have performed Rayleigh-Schrödinger perturbation theory. Because with Rayleigh-Schrödinger perturbation theory, what we will get then is something which depends only on the unperturbed energies. And then we can calculate everything order by order. Now, for the sake of completeness, I'm just going to list the contribution to third order. So let's do that. So we have a delta E3, which now is going to have a sum over these many body states, M and N. and they're both different from 0. And then we are going to have a phi 0. There's an H1, and then we have a phi of m. We have a phi of m of the m here, and we have an h of I of phi of n. And this is multiplied with phi of n of h of I and phi 0. And this is again divided, everything is divided with E minus W of M multiplied with E minus W of N. And then you see the pattern when you go to higher and higher order. It means then that you can define the wave operator to given orders in the interaction. So if we look at the wave operator, let's just list this for first order. So we would have a wave operator to first order in Brillouin-Wigner perturbation theory. And that's going to look like as a sum over m different from 0. And then I'm going to have a phi of m. We'll have my phi of m. And then I have a matrix element, h of I and phi 0. And this is divided by E minus W of m. And then if you go to second order, then you can actually look back at the expression we have for third order in the energy. So remember now that second order for the wave operator corresponds to third order in the energy, because then we are multiplying with hi, and we are taking the product with phi 0. So that means that we would, to third order, we would simply have the quantity which you see here without this part here. So you see here now that when you want the energy to second order, you're just multiplying in here with hi, and then you calculate the expectation value with phi 0. Okay, so the thing which we didn't say anything about is actually Rayleigh-Schrödinger perturbation theory. So if we go back to that, because now we can, let me just say one thing before I forget it, because we can rewrite the Brillouin-Wigner perturbation theory results in a more compact way. And this is something which I'm going to leave as an exercise to you. If you look at this sum, which you have up here, this sum which we put here, you can actually resum this one, this delta E, and you have a much more compact expression. And this compact expression which we get, and I leave that as a small exercise. This is now given by phi 0 of h of I plus q, and then you have 1 divided by E minus h0 plus, or minus actually, of q of h of I of q multiplied with q and multiplied with h of I and phi 0. So if you can calculate, this is a much more compact way of doing that. If this space Q is a finite space, and you can invert this matrix here, if you can invert that one, and then you can calculate the contributions to infinite order in Brillouin-Wigner perturbation theory. The only thing then is that you rely on having this need to put in a guess for this quantity here. And typically you would solve this iteratively by starting with different guesses. And then if the energy doesn't change more than a given quantity you have decided upon, then you would stop the iterative process. However, this hinges all on you being able to come up with a reasonable guess for the energy. Now, what Rayleigh-Schrödinger perturbation theory does, on the other hand, is actually to allow us to calculate order by order all these terms without any unknown quantities. So let's just put that one up here. We're just going to use the acronym RS. So in this case, what we do now is that this quantity W, which we have, is given by the energy of the unperturbed energy of the ansatz for the ground state. And if we do that, if we now plug that in, we are going to get the following expression. So if we now look at the energies, if we take and multiply with the, just bring back the expression for the energy here, what we have then is a sum over I equal to 0 to infinity, and then we have phi 0, and then we have h of I, and this is multiplied with this operator q, but now we have W0 minus H0, and this is multiplied with H of I, but now we get minus delta E, because we decided, so this is to the power of I, and this is multiplied with phi 0. So remember that what we had here was actually omega, this quantity omega, minus E. Now, if we put that one equal to W0, then we have W0 minus E, which is our definition of the negative correlation energy in perturbation theory. So what we have now is something which depends on the quantity which you see on the left here. So how can we actually do something meaningful with that? Now, there's one thing we need to look at now. So if we look at the last term here, this term here, acting on this one, if we write it out, this is just an intermediate step. If we take Q and multiply that with delta E and look at this expression here, this takes a value which is interesting for us. Delta E is a scalar now, just a constant. So what should this one be? If you remember the definition of Q.
0.
0, exactly. So delta E is just a scalar. Because it's just W minus E here. So that is something which we can use now when we are writing out this expansion. So if you look at the expansion, if we write it out, so let's keep this as an intermediate step, what we get is a phi 0 of H of I, phi 0. So this is as before, nothing new there. If I take the term to a second order now, this is going to have a HI minus delta E multiplied with HI. So we are going to get a plus phi 0, and then we have HI, and this is multiplied with Q divided by omega 0 minus H0. And this has now HI minus delta E. So this will be our second order term of phi 0. And we see now that the last term is actually 0. Now, when we now go to higher terms, what we get then is something which is not necessarily going to be equal to 0 when we take this delta E term, because what we will have then is H times Q of omega 0 minus H0. And now we're going to have H of I minus delta E. And then we have a new term, which is given by Q of omega 0 minus H0 multiplied with H of I, because this term here also becomes 0 because it's acting on the ground state ansatz, and the operator Q is orthogonal to that state. So we are now getting an additional term here. And we can have higher order terms here. Now, what we can do then is actually to regroup this in terms of the powers of the interaction. So if you now look at the first order term, which you have here, this term here, I now require that this term here should only contain the interaction to third order. So that means that I can rewrite what I have here as a sum, where I now have delta E, again, is going to be equal to delta, this sum over I equal 1 to infinity, and I have this delta E of I, and then I have my delta E of 1 is going to be the same as we had in Brillouin-Wigner perturbation theory. This is just phi 0 of H of I of phi 0, and we have calculated this many times. Then I have my second order term. And the second order term now is simply given by the quantity which we see here. And it simplifies because this delta E term is 0, gives 0. So what I get is something which is almost the same as we had in Brillouin-Wigner perturbation theory, but there is a small difference. So I'm going to have a sum over M here. So now I'm writing it out explicitly. So I have my phi 0. I have my H of I, phi of M. And then I have my phi of M here. And then I need a little bit more space of H of I of phi 0. And now I'm dividing this with omega 0 minus omega M. Now the third order term, if I just write this out in a more compact way, the third order term is going to be given by phi 0 H of I. But now I'm going to have this operator Q of omega minus H0. But we have to be a little bit careful now, because what I'm going to do is to replace in here a term which goes like first order perturbation theory. So that means that what I'm going to have is that this will be multiplied with H of I minus, and then I have an expectation value. And again, this is just a constant. And then I have Q of omega minus H0. And then I need a final term, which is HI, and multiplied with phi 0. And then this just continues to high and high order terms. Now, this term, which you see here, is going to be a little bit problematic for us, because it's going to give rise to something which is called poorly violating terms. And we have to figure out a way to deal with that. However, if we now stop at second order, this is where we now can do a lot of analysis. So we said now that the correlation energy which we have is just this sequence of terms. So the sum of terms from I equal 1 to infinity of delta E of I. And if we now look a little bit closer at the connection with the FCI calculations, then we see again that if we want to have a link with FCI calculations, we need to plug in the first order term in the reference energy. So this is the same as we had in discussion with Brillouin-Wigner perturbation theory. But let's now take a look at the term to second order, because that's the more interesting one. And then we just write it out now, and then we are going to analyze it after the small break. So this contains a sum over all states which are orthogonal to the ground state we've chosen, the ansatz. This contains the ground state, phi 0, and then I have an H of I, and then I have my phi of M, and then I have my phi of M, HI, and then I have phi 0. And this is now divided by omega 0 minus omega M. Now, when we look at this denominator here, this is something which is going to simplify for us in terms of a single particle basis. And we will see that after the break, because now we need to say a little bit more about what kind of states can these be. So the only thing we said is that this phi of M, they're just many-body states. So these many-body states could be one particle, one hole excitations. It could be two particle, two hole excitations, three particle, three hole, etc., etc. So if you look a little bit closer at this term, and this is something I'm going to leave for you now before we take a break. So this phi of M, which we have, this could now be given by all the particle hole excitations. But now we have to be careful, because there is no coefficient. The coefficient is something when we made the expansion of the ground state, the exact one, in terms of an orthogonal basis. But now this is just a plain Slater determinant. And this could be this guy here, right? Which we have met before. And this phi of I of A is nothing but A of I AI acting on the ground state. So that's one possibility. Or we could have a two-particle, two-hole. So this is a one-particle, one-hole. Or we could have an AB, IJ, and then we would have this guy. And then we know that this function here is nothing but an AI, AA, AB, AJ, and AI acting on phi 0, as we did in connection with the first midterm, and also when we discussed the FCI theory. So we have already calculated these matrix elements, and we know that in this specific case, if we limit ourselves to a two-body interaction only, it means that the overlap here with the states of a three-particle free-hole excitations are going to be 0. So this sum, due to the character of the interaction, is going to limit the contributions only to one-particle, one-hole, and two-particle, two-hole excitations. So when we do many-body perturbation theory to second order, we catch one-particle, one-hole, and two-particle, two-hole excitations to a given order. We don't capture all of them, but we capture them to second order. So you see, we are baking in we are obtaining the type of correlations which we had like when we did an FCI calculation. And the benefit with this type of calculations is actually that these matrix elements are normally matrix elements we can tabulate and just fetch from a table or calculate on the fly. And these denominators are going to give us some nice analytical expressions, which are easy to evaluate. And now we should take a break. We started a little bit late, so I hope it's okay if we now just stop now a little bit later, and then we can just stretch legs. Okay, so what we're going to do now is to look at these specific terms and see what we get to second order in perturbation theory. So we're going to wait with the higher order terms when we are going to discuss a diagrammatic representation, because then we are going to visualize diagrammatically what these Pauli violating terms mean. If you go into the textbook by Sherwitt and Bartlett, you will actually find a whole chapter which is dedicated to Pauli violating diagrams. But we haven't discussed the diagrammatic representation yet. We're going to bring that up next week. But today I just wanted to go through the equations, because at the end, this is what we are going to program anyway. And I was actually thinking that the second midterm which we have could deal with things which rotate around this, and maybe also copper cluster theory, where we can take a simplified Hamiltonian, or we can just look at matrix elements and then just read them in, and then calculate these terms and see how they eventually improve, let's say, a Hartree-Fock calculation. Okay, so let's now go back a little bit and look at these matrix elements. So the first order term, which we had, is pretty easy. So this is just the term which you see here. And that's something which we have calculated in the very beginning of the semester. So we are not going to repeat that calculation. We know the matrix elements. And actually, we have calculated the other matrix elements as well. So one thing which we said now is that when we look at this specific sum, we are now going to sum over one particle, one hole excitations, two particle, two hole, three particle, three hole, etc. That's the way we organized or regrouped this set of Slater determinants, which are not included in the ground state. If you have a model space which is larger than 1, as dimensionality larger than 1, then we can actually mix in other states. And there you could have a mixture of the ground state with one particle, one hole excitations. And then the rest of the states could be the excluded space. So this is very much up to us, how big a model space we want to handle. The whole idea with a model space is that we want something which is small and tractable. That defines an effective Hamiltonian. So let me also mention that one before we move on. If you look at this wave operator, which we defined before the break, so let me just bring it back here. This wave operator here, if we now multiply that with h of I. So if you take this term, which you see here, this one, and multiply that with h of I, like we are setting up here, that defines your effective Hamiltonian. So that's an effective Hamiltonian now, which incorporates excluded degrees of freedom. So it's a way to build up a Hamiltonian, which now acts in a smaller space. And then it takes into account all these excluded degrees of freedom. And we normally call that for an effective Hamiltonian. So let me just have that as a small digression, because this is something some of you may encounter when you deal with many-body methods applied to, let's say, atomic physics, molecular physics, or nuclear physics. And I know that one of you has taken a course in nuclear physics, or is taking a course in nuclear physics, and then you have encountered effective Hamiltonians. So the machinery which you see here, if I now take, so let me just remind you of that. If I just take and multiply hi with omega of E, or the effective, or the wave operator, which we have in Rayleigh-Schrödinger perturbation theory, this defines an H effective. And clearly, where you truncate obviously defines your approximation. Now let's now take a look at the explicit expressions in Rayleigh-Schrödinger perturbation theory. And let's look at the case where phi of m, so since we have decided that the interaction is just a two-body interaction, that means that we have no free particle free hole excitations or higher excitations. That means that we can start now with this state here, for one particle, one hole excitation. That means that the sum over m of phi of m multiplied with phi of m, that becomes a sum which now runs over a and I of the state phi ia multiplied with phi ia here. So this is just the outer product of the two vectors. And that is a matrix, right? So what this means is that the contribution to the energy is now going to be given by a sum over A and I. And I'm going to have a contribution I, and this operator, let me just, before I do that, let me just write down the general form of the matrix elements. So it's going to be a phi 0 of H of I, of phi I, A, multiplied with phi 0, no, sorry, phi IA of H of I. So we have to be a bit careful because this is now the two-body interaction or the interaction part of the Hamiltonian. So it doesn't include the single particle piece of the Hamiltonian. And then this is now multiplied with phi 0. And then when we look at the denominator here, this is now going to be given by omega 0 minus. And let's take a look at what this term is. So let's take a closer look at that one, because this is going to simplify the denominator. So this term is given in by this expectation value here. And that expectation value contains the energy of the ground state, omega 0, but where we have removed one of the whole states, and we have filled in, so that a whole state has now been, the particle in the whole state has been promoted to a particle state, A. So that means that we have to take out from this sum omega 0, this specific state epsilon of I, the energy of that one, and then we have plus epsilon of A. Does that sound reasonable? Now, and what you see now is that we have W0 minus W0 minus epsilon of I plus epsilon of A. So that means that the denominator is now simply going to contain the single particle energies. Now, we have to be a little bit careful with things now as we are moving into actual calculations. So let's assume now that what we have is not a Hartree-Fock basis. So let's stay with just a basis which is an eigenbasis of H0. And that means that now we have to look at the terms which we get here. So if we now write it out, what we will have is a sum over AI, and the Hamiltonian is emission, so which means that I can actually write this out as a phi 0 of H of I, and then I have phi of IA squared divided by epsilon of I minus epsilon of A. Now, we have already calculated this matrix element. We did that one in connection with Hartree-Fock theory. The only thing which is missing now is H0. So what this one is going to give us, so you remember now that when we looked at the Hamiltonian, which was normalized with a given vacuum, that included also this single particle piece. But note now that what we are doing is just an expansion in terms of the interaction itself. And that interaction matrix elements in that case, if we now look at that piece, that's going to contain this operator when that is normalized to a given system. This will now contain a sum over J, and then we're going to have an A, and let's now put in the matrix elements here. So it's going to have an operator. Let me just bring it up properly. So there's going to be a sum over P and Q. And then we're going to have an operator, AP, AQ, dagger. So we have to be just a little bit careful because now we are dealing with a matrix element which is now prepared for a given vacuum reference state, but it contains only the two-body interaction. So instead of using that operator F, which we put up, I now need to single explicitly out the interaction piece in F. So that will contain a one-body piece, and that contains a sum over J. And then I have the matrix element Pj, V, and then I have Qj, anti-symmetrized. And then I have the two-body term, which is a sum over 1 over 4 of PQRS. And then I have my AP dagger, AQ, AS, AR. And this is then multiplied with the matrix elements PQ, V, and then RS, anti-symmetrized. So if I now take a look at this matrix element, what I need then is phi 0. And what I'm going to do here is simply to take the operator structure. So I'm just going to skip the other terms. So I need to calculate AP dagger, AQ, and then I have my state, which is an A of A and A of I acting on the vacuum state. So that is one term, and we've already calculated that one. So we know what that should be. So the only possible contraction is actually this one, this set of contractions here. And then when we look at the two-body piece, or the one which has two creation and two annihilation operators, this is also something which we calculated earlier. So this is my R and my S, and then I have an AA, A of I, phi 0. We know that this one, since we end up with two sets of operators which have to be contracted within the same chain of normal ordered operators, this is actually the last term here is 0. So this is 0. And this one gives us delta Q of A and delta P of I. So what we have then, for this specific term, we get a contribution which runs like delta 2, and this is given by a sum over A and I, and I have a matrix element, which is given by the interaction matrix element. Let me just write it out here properly. So this is also going to have a sum over J, and it's going to be given by the matrix element squared, and then I have my I, and then I have J, V, A, J, anti-symmetrized, and this is squared, and this is divided by epsilon I minus epsilon A. This quantity which we have here is the Hartree-Fock potential. And we can rewrite this one as a sum of A of I, and then we have I U Hartree-Fock, as we defined when we looked at Hartree-Fock theory with A, and this is squared, divided by epsilon I minus epsilon A. So that's the first term. So we have to be a little bit careful, because what we need to look at is the fact that we now have a matrix element which contains only the interaction piece. And since we have defined the unperturbed operator, we have to be a little bit careful on where we place different terms of the unperturbed operator. So our Hamiltonian, our normal ordered Hamiltonian, contains this specific term which we have here, that one. It contains a plain one-body term with no interaction, plus the two-body term here. So we just need to pay a little bit attention, because we have changed a little bit the way we define quantities here. We have a perturbative expansion in the interaction only. So next week, we're going to look at the way these quantities look like when we look at the diagrammatic expansion. Then we can take the next term, which now contains the two-particle two-hole state. So that means that the state phi of m is simply given by a phi I j a b. That means that the sum which we had over m now goes over, is replaced by a sum over a and b and I and j. And if we now do the calculations, what we're going to get is a sum over a, b, I and j. And then we are going to look at the matrix elements of phi 0 with h of I. And then we have phi ij ab squared divided. And in this particular case, what we get now, since we have removed two particle two-hole states, we get an epsilon I plus an epsilon j. And then we have added these two particle states. So the denominator is easy to calculate. And this denominator could be the denominator which has as input the Hartree-Fock energies. So we can leave that unspecified. The only thing we have to be careful with is when we now are setting up h of I. So in this case, what we have to calculate now is phi 0 of h of I, and then we have a b dagger, aj, ai of phi 0. And this is also something which we have already calculated. And if we now go back to what we had as a definition of the Hamiltonian, and then just remember what we did in connection with both full configuration interaction theory and Hartree-Fock theory, we know that if we have a one-body operator, like this term here, and we have so the one-body operator acting on a two-particle two-hole state will always leave a set of creation and annihilation operators uncontracted, and that will give us 0. So the only term which gives something which is different from 0 now is going to be a term which comes from the interaction here. So that means that we can now, if we go back here, we can now start looking at the following term. So the contractions which we need to think of are the contractions AP, and we have calculated this already, but I'm just going to repeat it, okay? So we did that in connection with both Hartree-Fock theory and the full FCI theory, when we computed the overlap between the ground state and a two-particle two-hole Slater determinant. So remember now that the way we have written this is just a way of rewriting many body states in terms of a summation of specific single particle states. So this contains an AQ dagger, and then we have the AR and AS and AR, sorry. And then I have my A, AB, AJ, A of I. So if you look at the contractions here, let me just repeat that. So the first one is actually this one. This is the simplest case. That one. And then we do this one with that one. And like this. So that's going to give us, when we do all the delta contractions, or the Kronecker deltas, we get a matrix element which runs like IJ, V, AB, anti-symmetrized. So we get the Kronecker delta with R and A, S and B, and then we have P equal to I and Q equal to J. So the matrix elements we are looking at are the matrix elements PQ, V, RS. So this is the first contraction, 1. And then the other possibility is now that R goes to B instead. And then we have a crossing fermion line here. So that's going to give us rise to a minus sign. And then we have this one. And then we have, sorry, not that one, but we have this one going to that one. So we keep the whole state to be the same. So that's going to give us a minus sign because we have to switch the operators A dagger and AB dagger. And that's going to give us a minus. And I have my IJ of V of BA, anti-symmetrized. Then I can keep this contraction between the particle states fixed. So I can keep that one. But now I can interchange the whole states. I did that one, and then I get a new crossing fermion line. So that's going to give me a minus sign and a minus sign. So that's a plus sign. So I get the JI V of BA, anti-symmetrized. And then there's a final possibility, which is actually given by these two guys here, as before. And then I have the whole states which get interchanged here. Like that, sorry. Let me just redraw it here. I got a line here which I didn't want. There we are. So we get this one to here, and then this one goes to the last one. So that gives me a minus sign. So I have J of I of V of AB, anti-symmetrized. And I know that from the properties of these anti-symmetrized matrix elements, if I interchange A and B here, gives a plus sign. If I interchange I and J and B and A, I get back a matrix element, which is IJ, AB. And the same with the last one, summing all of them just gives me 4 contributions. Then what I have to pay attention to is that I have the matrix elements squared. So each matrix element here contains a factor of 1 divided by 4. But the only contractions I can make are these 4 possibilities. I have the matrix element squared, which means I have a factor of 1 over 16. And then I get these 4 matrix elements, which sum up to 1. So that means that when I plug everything in here, what I'm getting is that delta E of 2 is going to be given by 1 divided by 4. And then I have a sum over A, B, I, J. And then I have my matrix elements, and I'm just writing out the matrix elements, A, B. And from now on, it's going to be clear that these matrix elements are anti-symmetrized. I'm going to skip the AS subscript because I will always use anti-symmetrized matrix elements. And this is given by epsilon I plus epsilon J minus epsilon A minus epsilon B. Now let's take a look now at what we had earlier. So if we go to FCI theory, what we found now is the following. We found that this delta E, when we collect all the terms, so we collect we have the following contributions. So we have A of I, and then we have the matrix elements I of, and this is the U Hartree-Fock of A of U Hartree-Fock of I divided by epsilon I minus epsilon A. And then we have an additional term, 1 over 4. And then we have AB, IJ. And then we have the matrix elements IJ, V. So this is now an approximative result because we have truncated perturbation theory at second order. And then I have the first order term. So I need to add, so the total energy, so E with Rayleigh-Schrödinger perturbation theory to second order is now going to include W0, obviously, plus delta E1 plus delta E2. Okay. So this is now the approximation I've made to perturbation theory. So this is my energy. My correlated energy contains now delta E2 plus delta E1. But if I now compare this with FCI, if I look at this delta E FCI, that contains now a sum over AI. These coefficients which I get from the CI calculation or FCI calculation, I, and now this contains F of A plus a sum over AB, IJ, CIJ, AB, and then the matrix element IJ, V of AB. Now we can start making comparisons. And now you will see that in perturbation theory, what we have is that CIJ, AB, which would be exact if we can diagonalize the problem. This is now a proportional or approximatively given if we now compare. So this is the FCI. And here we have the many-body perturbation theory piece. This one is now given by my term AB Vij divided by epsilon I plus epsilon j minus epsilon A minus epsilon B. So this is the way I can now interpret these coefficients. Remember, these coefficients are dimensionless, and you see now that we have dimension energy in the denominator and dimension energy in the numerator. So that fits. And then we multiply with energy, which is the matrix elements. If we assume the matrix elements carry unit, no dimension energy, then we get the right dimensionality here. But you see now that this gives us a nice connection with the FCI calculations. The thing which is interesting here now is that if you look at the expressions which we have, what we have is we have, instead of a diagonalization problem where we could have a monstrous basis, we are now simply summing over single particle states. That means that many-body perturbation theory, we can have a larger single particle basis than you would be able to deal with in a diagonalization problem. So the benefit of doing this is that you can have a much larger single particle basis if your result is sensitive to the tails of the wave function. So you have a much larger set of Slater determinants, which include the cons in this specific case is the fact that you don't know whether many-body perturbation theory converges. You may get a reasonable result to second order, and then third order may ruin everything. And then fourth order may bring you back to a reasonable result, and then fifth order may ruin everything again. So this is something which you don't know a priori, whether it converges or not. But normally in fields like atomic physics and solid state physics with weakly interacting systems, this normally works pretty well. So combined with a Hartree-Fock basis, this is something which now allows us to make approximations to the theory where you can have a much larger single particle basis. So the benefit here is a possibility to have a much larger single particle basis, which means that you sum over many more two-particle, two-hole Slater determinants.
That's weird. You add the degree of perturbation and it gets worse.
You don't know, because it depends. If you look at what you have here, it's the ratio between the strength of interaction and the single particle spacings. So if the interaction is larger, so suppose now this term which you see here, this term here is larger or equal to 1 in absolute value, that will lead to problems when it comes to the convergence of perturbation theory. If this is a small quantity, adding higher and higher terms is going to give you smaller and smaller contributions. So the strength of the interaction plays an important role.
Does the spacing of the single particle energies also, if
Oh,
they are
yeah.
very, very close?
Yeah. Then this breaks down.
Yeah.
So if you actually have a system where you have, suppose you have a harmonic oscillator and you make the harmonic oscillator wider and wider, that means that your harmonic oscillator frequency is very small. On average, the particles are far apart from each other. And then you would expect that these matrix elements would be small. But what happens then is that your spacing around the Fermi level goes to 0. And that means that this denominator blows up. So you get this kind of paradox that the interaction can be weak, but due to the spacing between the single particle states, your theory doesn't converge. So you can actually, by looking at your physical systems, you can say that for this specific system, if I am going to look at ionized sodium, where I know that the first state above the Fermi level is a free s electron. If I kick that away, I have only a closed core with up to 2s and 2p. The gap there between the 2s and the 2p is normally pretty large. And that means that I can actually use perturbation theory here. And that makes perfectly sense. Actually, Hartree-Fock calculations brings you pretty close to the final result. Now, the thing we have to be a little bit careful with here when we make this interpretation is actually the connection with the matrix elements you see here. Because this quantity which we defined here, this F, that contains the H0 operator as well. So F has the U Hartree-Fock, but it contains also the single particle states, which we include here. So there is not a direct connection between this one and what you see here. So the thing you would have to do is actually you would have to single out here the one body term, which gives rise to the, let's say, the harmonic oscillator potential, or just the potential without information about the system. So just be careful with that, that in case this F, we want to make a direct comparison between this coefficient and the coefficients you see here, we would actually have to add and subtract a term here. But that's fully possible. You would just carry with you another term, which is easy to calculate, and which is actually 0. Because if you think of these A's, if you haven't done a Hartree-Fock calculation, these A's, so let me just explain that. So if you look at F, this I of F here, of A, this is given by I of H0 times A, right? Plus this term, which we call the Hartree-Fock potential, which now contains the sum over J. So this will be Ij, V, A, J here. So if and I don't need to have chosen a Hartree-Fock basis, but this could now be given by A of A plus this I of U Hartree-Fock, as we called it, of A. Now, if these states, A and I, are eigenstates of this one, then we know that this matrix element here is by definition equal to 0. That means then, if that is the case, that means that our CIA in CI calculations, so this is the FCI case, can then be approximated with I of the U-Hartree-Fock of A divided by epsilon I minus epsilon A. And then we made the connection between the FCI calculations and the approximative method given by many-body perturbation theory. Now, when I bring in higher order terms, I will get more complicated coefficients. And then clearly what I would have to do then would be to reinterpret the wave operator, because when I look at the wave operator to second order is now going to contain matrix elements to higher order. So if you look back at what we defined as the wave operator, if I now were to stop at third order, so we defined the wave operator a little bit earlier here. Let me just bring it back. Why did I define it? I thought I had written out the wave operator to a given order.
Yeah.
That's the wave function.
A little bit
Up or down now?
and maybe past it.
I thought I had defined it
Yeah.
explicit.
Sure.
Yeah. So if you go to third order, then you would now have this term, that one. So your coefficients Cij AB would now, in addition to this term which we analyzed, it would also contain this term. So you're adding more and more terms to your coefficients, and at the end, if you were able to sum to infinite order, then you should get the same as FCI gives you. So you have to view this as an approximation, what we have extracted here. And if many-body perturbation theory is a good approximation, then we probably get something which is close to the FCI calculations. So next week, we are going to look further at these things, and we're also going to look at the diagrammatic representation of these different terms here. And we are going to dive a little bit into a diagrammatic interpretations, and we're also going to look at these Pauli violating diagrams. Now, when you do copper cluster theory, this is pretty similar, because in copper cluster theory, you're going to have an expression for the energy, where you also have an approximation in terms of this and that. And then it's pretty normal, since this is a set of nonlinear equations in the unknown coefficient C of I. Then, since this is an nonlinear expansion, your first iteration is normally given by this ansatz which you see here for the coefficients. So this ansatz to many-body perturbation theory to second order is often used as a way to initialize an iterative process, which leads to a many-body method like copper cluster theory, which is where we probably will end this semester. So I hope you see the links between many-body perturbation theory, FCI theory, and Hartree-Fock theory. Because if you have a Hartree-Fock basis, then these matrix elements I, F, and A, they're going to be zero. I'm going to stop the recording here.